Good. So we are yes. Previous time we talk about generally about network design, set of problems that there is a network or graph is involved and lots of parameters of this network and graph is there as well. Then and we talk about some basic problems. We started with some kinds of covering problem, in particular about 3 problems, which are basics of any network. And we talk about the application. This is a set cover, maximum coverage, and last but not least, unique coverage. All of them have lots of application in wireless networks. Essentially, the general idea is that you want to cover some area with some kinds of wireless antenna. How can you cover everything? You want to cover with limited resources. Cover everything would be set cover. Cover with limited resources would be maximum coverage. And covering while you are essentially try to decrease the area of interference, then it would be unique coverage. And these are applications that are actually the thing. At the same time, these are very famous problems that they have tons of applications and the people have used them. So they have, this is just one application of that or a application. There are lots of other applications and these are very fundamental things and we are discussing some of them here. So here, let's start here with the, like, or continue this with so we are continuing today with submodular set cover or just submodular cover, which is a generalization of set cover. We have also described the greedy algorithm for set cover, and we went through that and why it is a log n approximation. We said that why it is tight, everything we discussed previous time, and as well as F approximation. Here we are talking about the generalization of that, which is a submodular set cover or submodular cover. So I think let's use this other one for now. What is the definition of submodular coverage? Just delete them. Okay, so we are talking about submodular cover. So let's assume that U is a finite set. Say U is a finite set. And if essentially is the one that considered for any subset of U, just take it to some number essentially. Say for now a non-negative integer values function. So here if have this property, if is non-decreasing, means that f of s is less than or equal to f of t for all s and t which are a subset of u, and s is a subset of t. Essentially, it does not, is increasing, I mean, say better than increasing, we'll just call it non-decreasing. And the other one, which is very important, is submodular. So what is a submodular? Essentially, it says that for any set s and t, f of s plus f of t is greater or equal to f of s union t plus f of s intersection t. This is for all s and t. So this is an important thing for submodular. And there is another thing that is also some of this result that we have it in these papers. Also, it can be used for some other problem like subadditive. Subadditive is essentially is a, as you see, the more relaxed version of that. Here we said that f of s plus f of t should be greater or equal to f of s f of s union t plus f of s intersection t. But here we say that it only should be greater or equal to f of s union t. And of course, this would be additive if this is essentially this, we have the equality here. But I mean, generally, these are the things. If you have two sets, I mean, generally for additive, also we have these things that they should be when they are there is no intersection should be equal to some of them. But anyhow, so for the sub-additive, this is a definition that we are using. It is more general than additive, and it says that f of s plus f of t is greater than f of s union t. And some places lots of places actually submodular works better. It has more structure to it, but sometimes we can also generalize this sub-additive. And this is a general interesting research direction. So when you solve some problem for submodular, you may think whether you can do something for sub-additive. Sometimes you can do it, not all the time, but sometimes you can do it. And that would be very interesting. Finally, and one important thing about another, this definition of submodular is a bit hard to work with it. A better, much better definition and something that you can check it essentially whether a function is submodular or not that we are using it. And this is the equivalent of that. Is that if you have two set essentially B and A, that B is a subset of A. Then, and say there is an element which is not in A. If you're adding this element to A, that should, the marginal means that adding f of this minus f of this A union non-capital A minus f of A, this is called marginal. If this marginal for a smaller set, here B is a smaller set, for a smaller set is always greater than or equal to the larger set. And this is it's a natural thing. Is that essentially once if the larger set, one guy you will add it, it should have less effect comparing when you have a smaller set and you are adding this guy. So in a large crowd, generally I have a less voice. And that's exactly the definition of submodular. And this is very natural. That's the thing that makes it very natural. It is a good exercise actually to show that these two are equivalent. From one, you can get the other one. But generally, the second one is the one that is much easier to check and much easier to, essentially motivate even this problem. Finally, we say that F is a polymatroid. If it is non-decreasing, as I have mentioned, it is submodular, integer valued, and f of empty set, this is the most important one in some sense, in addition of this other thing, that f of empty set should be 0. And let me just check one thing I wanted to see. Yes. So this is the definition of submodular. Continuing for this, let me clear everything. Good. Now let's go to submodular setcover, which is generalization of setcover. So here for this one, I'm just putting it a little bit down. Yeah. So here you are given a submodular set cover problem, or just submodular cover. There is no need to say set. There's a universe U. This is the same as set cover. We have a universe of elements. A non-decreasing submodular function. That's the one that here. So it's non-decreasing as submodular function. Again, she's defined on all subsets of U. And it goes to essentially positive plus 0. And it is a cost Ci for each element Ui. So for each element, we have a cost essentially. Good. So usually can go there. So you can, I mean, just see here that, so for a finite set U and this non-decreasing submodular function, if there is a non-negative cost Ci associated with each element U, and the cost of a subset of S, so the cost of a subset would be just sum of the cost of the elements. So that's a typical thing that we are asking. This is the additive essentially. A subset S, which is subset of U, is spanning if f of S is equal to f of U. F of S is equal to f of the whole element. Then the problem asks for a spanning set S star such that the C of S star is minimum. So this is a submodular cover problem. Again, given I mean this U function that this U set and this function F, which is non-negative, you want to find a spanning set S star. It means that f of S star should be equal to f of the whole U. And at the same time, you want to minimize the cost of S. And the cost of S here essentially just sum of the elements on S. You can possibly actually, there might be some definition like this that you can also, the cost of S star itself, it might be a submodular function. I believe there are some studies like that. I don't remember the exact thing, but currently we are considering that the C of S star is just sum of the elements. Good. Let's actually go there. And I wanted to give, this is actually interesting thing. Clear everything. And then, good. So let's first say that why this problem is actually is a generalization of setcover. How can we solve a setcover? Again, what was setcover? Setcover, the thing that we have it, we have again, we have this U, and we have a set of subsets, S1, so Sn, these are subsets of U, and you wanted to select a set of S1, a subset of them, subset of these guys, such that their union, so essentially you want to use S prime 1 to S prime k, either among this one you want to say, I mean the minimum number of sets, such that the union of these guys is equal to U. And you want to get, say, minimum, so if each set has a cost, then you want to get the total minimum cost, or just even the minimum number of sets such that their union is equal to U. So this is a set cover. We want to say that how come this submodular set cover or submodular cover actually is more general than that. So as I mentioned, so this is the, so for set cover we have U and we have S. And we have also for this S, we have a cost function. The cost function for each set S, it essentially gives some real number, some real positive or zero. So no negative things. So this is the way that we can define. So let's define, so, and this is a catch. So here, U would be different. U would be S1 to Sn. So U will be not the same U that we had it there, essentially. And that's the thing that we are using different shape of U here. So U in this, so this is essentially, this is submodular set cover. So here the U would be S1, S2 to Sn. These are the sets that you had it in the set cover. Now Ci is the cost of Si, which is given by C of Si. Good. So as I mentioned, for each, so in this submodular set cover, for each of these elements which are now sets, we have a cost. So Ci of the cost of Si would be essentially the cost of C of Si. Now, what is the f function? The f function is, what is f? Essentially, so that what about for any subsets? Now, any subset of U would be a set of subsets of the original set S. In this case, for any essentially set of S, which is a subset of S and contains these elements, we define f of S as the size of their union. So just take the size of, so again, here the U in the submodular set cover, actually each element is a subset of the original set universal U that we had it before. Now, for any subset of this U in the submodular set cover, we are defining the f function, which is the size of their union of all these elements. Good. Now, what would be the f of U in this case? F of U would be actually M, because if you take all these subsets, the union of all of them have all the M elements that we originally had as the universe in the set cover. And here, what do we want to find? We want to find a S star. What is the SS star? SS star is a subset of this, essentially subsets of is a subset of U, which is indeed a set of subsets in the set cover problem, such that the union of such that f of f star, which is the union of all the elements, the size of it is equal to f of U. It means it's equal to M. Essentially, here we want to find a set cover problem. So this is the thing that this submodular set cover actually is a generalization of set cover. It's even a bit non-trivial, it's a bit tricky. It's not just like, if you consider U is not the same U. You need to go from elements to sets in U in submodular. From elements in set cover, you need to go to the somehow the sets in the submodular set cover as the elements. But that's essentially the things, and you can show that here, this is the F. By the way, we need to also say F is a submodular things. That is always, it is easy with that definition that I have mentioned, the marginal things. If you consider two sets, and if you, to the larger set, if you add a set, it has less, it will add less to the size of the total union. Why? Because some of these elements might be covered in a more, and again, the first one is a subset of the other one. So comparing, if this is a subset, the other one is like a bit more general, we probably covered more. So if you add a set to these larger sets, probably in terms of the size of the union, you will add less. Or the same thing. So that's the thing that it is submodular. So this is actually like very interesting, because using this, lots of other problems, this was like the thing. So there was a set cover problem. Set cover is a very important and famous problem. The people actually worked and tried to, if lots of people, I mean, may not know that, then they are considering a new problem. And this new problem, they try to design a new algorithm, log-n approximation. As we discussed, for set cover, there is ln of approximation, and this ln of approximation is actually tight. You cannot even get, I'm not talking even about the constant. It is just ln of n. We cannot get anything better than constant. Better than ln of n. Now, having said that, the people, I mean, different problems, set cover is a very famous and is a very strong problem. Lots of problems seem very similar to set cover, and the people will come and then design a set cover greedy algorithm, and they publish a paper there. However, this is interesting. Almost all of them are, or lots of them are, just a special case of this submodular set cover, as you will see. And it is sometimes it's quite non-trivial to see that. You really, and you may need to design a little bit different algorithm actually to do that. But they are all subsets of these things. I will give Let's say what is the algorithm for that, and then we will go from this. Good. So this approximation algorithm for submodular setcover, which is actually goes to Wolsey or Wolsey 1982. That's actually a very important theorem. It says that if f is a polymatroid function, and polymatroid function essentially means that also f of, again, f of empty set is equal to 0. So if f is a polymatroid, things, and as we mentioned, polymatroid, it has this condition that it should be non-decreasing and submodular, etc. In addition of this property. Then there is a h. H is essentially harmonic number. The harmonic number of max of j belongs to u, f of j. Like consider individual elements in j and say what is f of those. Max of them and the harmonic number of that, and all of them are integers. So each of that, which would be essentially, I mean, the harmonic number would be just some log. So it would be order log of max of j belong to u, f of j. There is a log n factor approximation of this with this log n factor of this for the submodular setcover problem. What is the algorithm? The algorithm is this greedy, very simple greedy algorithm. You will start with a C0, a C empty set. You will add gradually an element uj, which minimizes this. So cost of cj, cost of cj divided by the marginal gain that c gives, that j gives to the cover c. So again, what is the algorithm? You are starting with, I mean, some essentially c equal to empty set. Then you are adding one of these elements to this c that minimizes this property. Cost of that over the marginal gain that it gets, it should be minimized. It's exactly very similar to this cost efficiency that we discussed for the set cover. If you remember previous time for set cover, we had this algorithm that here you want to, what was the set cover? So you are starting with no set selected, then you will add a set that the cost of the set over the number of newly covered elements is minimized. That's the one that I mentioned, the most cost-effective thing. And we called it alpha. And then in the analysis, we gave this alpha essentially to each of these newly covered elements. And we showed that the cost of our algorithm is at most log n times the, or ln of n times cost of the optimum. So the proof is very similar to set cover. I do not repeat. You can actually go and read the actual proof if you want, but it is very similar to set cover, and it would be a good exercise actually to prove it yourself, given the proof of set cover that we discussed before. And these are all available both in the recording as well as in the lecture notes. So this is the algorithm. It's a very natural algorithm again. You will add the one that the cost of that over the marginal gain is minimized. It means that the most cost effective. And you will repeat until you will repeat this one until f of the c is equal to f of u. That was exactly until you will find essentially the optimum solution. Because that was the definition. The submodular cover, you want to find the S star, that f of S star is equal to f of u. And because it is non-decreasing, you know that f of u is maximized. So you will continue this one until, so do this one until f of c is equal to f of u. Again, the unlimited is very similar to that. Now, this problem actually, lots of other variants that you are considering, it would be, if you want to design this algorithm yourself, it would be non-trivial again. But you will just use this theorem and you can solve it. Let's see this problem. So here, the main interesting thing here is this F things that this submodular function. How should we, the main innovative part here is that how can you define this submodular function? Let's see an example here. Good. So let's consider a variant of set cover, which is called two-set cover. What is a two-set cover? There's a universe U. Again, this is a set cover instance. A universe U of all the elements, and the collection S of the subset of U. And for each of them, there is a cost. Say a positive cost. Because if this is a negative cost, you can always select that set. That's the reason that the set cover is actually interesting, where all the costs are essentially positive or zero. Or even actually, I will say positive, because if something is zero or negative, you just take that set, that's just beneficial, and then you need to solve the rest. Well, is set cover related to cover anywhere related in math? Set cover is actually there are some variation intersection, but it is generally different. Yeah, and NAFSAC is generally more like a constant approximation. This is more like an approximation. Good. So you want, what is the goal? So you want to find a minimum cost S prime such that each element of U occurs at least twice in their union. Good. So in the set cover, you want to cover all the elements. You want to make sure that all the elements are essentially one set contained. Here, I want to have these other things, that I want that each element, I want that two sets covered. It changes the problem, you know. When you add such a small changes to the definition of the problem, it actually changes quite a bit the problem. But now we can see actually this problem, we can use the submodular set cover and solve it easily with that. And it should be, again, the definition of F is non-trivial. So again, so the problem is set cover. You want to find a set of subsets such that each element is covered twice. Again, you can consider some wireless network or something that you want to have some backup for each set. If this antenna went down, there is another antenna. So we want to essentially use the here we want to use the same that theorem that we have discussed. So we need to define, as I mentioned, an appropriate function S. Let's at the first attempt say that, okay, you are selecting so we know that again in this U, in the submodular cover, this would be essentially S1, S2 to Sn. So these are the subsets that are given in the submodular, in the set cover problem. Now, how can we define f of s? F of s, and of course, these are, say, this is the universal. I will say this is the universe. I will call it universe instead of just U. So universe was essentially, I don't know, U1 to UM. So we have these elements, and these are the subsets in the set cover problem. Now, in this U in the set cover, in the submodular set cover, would be S1 to Sn. Now, what is f of S? And f of course, S itself has a, say, let's call it cal S. What is cal S? So cal S is actually is a subset of them. So Si1, Si2, and then Si. So a subset of this set system. So f of S, we can say that as say is the number of elements which belong to at least two of these guys. Good. So we can define the coverage of this S to be the number of elements which are essentially covered at least by two of these. This is a very natural thing for this. So you can check that then in this case, F is not submodular. Why F is not submodular? Because it might be the case that, like, for example, there is one element that is, say, covered. So say this is, so why this is not a submodular function? So there is a one element here that we always consider this B, which is a subset of A, correct? In the here in A, this U is covered by one of these sets. But in B, it is not covered by anything. Now, if you add U to A, then it is covered twice. So then you will get +1 here. But if you add it to B, then it is only covered once. So you don't get anything. So this is submodularity essentially is violated. To a larger set, when I add it, I get more gain sometimes than this. Not always, but sometimes. So this is not a submodular function. In some sense, it should be a smooth function. How can we define this? We can change it and define it this one. F of essentially this is callous essentially. So we define the beta of ui is 0 if ui is not belonging to any of this. So I'm changing the function. So p of ui is 0 if ui does not belong to any of this. Like beta of ui. Beta of ui is equal to 1 if ui belongs to exactly one of these guys. And if it belongs to more, at least 2, then it would be at 2. So the value would be 0, 1, and 2. So in some sense, we have a progress 0, 1, 2. Above 2, then we don't care. Then you can show that this F is a submodular function. Why? Again, now you can see that if you are adding an element to a larger set, actually there is some, it may be less benefit because if this previous case that I have mentioned, this U belongs to A, so there was a U that, so U belongs to A, but U did not belong to B. So in that case, there was this element like this. So this element that was belonging to A. Now, if I add U, here I get, okay, +1 because covered 2, but here also get some credit because it was not covered and covered once. Now it is plus. Now, what would be the F of U? F of U essentially would be 2 times M, not M anymore. Because for each M, we can have at most, we should, and we are assuming that, by the way, you should have this property at the beginning, that each element should come at least in 2 sets. Otherwise, the problem does not make any sense. So if it is the case, F of U would be 2 times M, and M it was the number of universe essentially in the subset, in the set cover problem. So F of U is 2M. Now, if you can make F of any S star, Chalice star, to becomes 2M with minimum S, that's essentially a solution for you. You see, this is not trivial. If you want to solve it as a set cover, you may redefine everything. But here, in some sense, everything nicely goes to this function. I will talk another one essentially about more general thing, which is also interesting and has applications in other places, is even more general than submodular set cover that has a network benefit. But here, one other things before I will go to this one. Let me just clear this. Go back to here. One important thing, note that here we talk about approximation factor here. And here we mentioned that the approximation factor would be the h of max of this, which is equal to order log n of max of j belongs to u f of j. No, in the set cover, it is what's important. What is f of here is f of the individual, guys. So if when you go from set cover to submodular set cover, then f of individual, guys, would be actually the number of elements that each of these sets have. So log of this, essentially, it would be the max size of S, where S is a subset of universe in set cover. So this is a very strong theorem. It said that, I mean, we don't get just log n approximation, or n is the number of sets. It said that for this, the approximation factor of this would be f of j. And f of an individual thing in the set cover is that how many elements it covers. So f of that would be essentially the size of the set. And the maximum size of the set would be essentially this max and the log of that. So if all the sets are small, this actually gets a constant factor approximation. For example, a vertex cover problem is a special case of set cover. In the vertex cover, you are given a graph. And let's say why it didn't go away. So in the vertex cover problem, this is a very important graph problem that we are working a lot with it. So it's very famous as well. So the vertex cover problem, in the vertex cover problem, you are given a graph and you want to find the minimum number of nodes such that all edges are covered. All edges here means that covered means that at least one of the endpoints are selected essentially. Good. So vertex cover is a special case of set cover. Why? Because all here, the elements would be essentially all the edges in the graph, E1 to En, Em, if we have M edges in the graph. So M is the size of E. Then in this case, what are the sets? So for example, each edge, each vertex would be so each vertex here would be a set, essentially, a subset of these guys. Like V would be the number of, so for example, for each vertex V, we have a set of the edges that it covers. So E1, EK, depending on the degree. So in this case, then you want to find the minimum number of V such that number of vertices such that you will cover all the edges. Because from each, but the catch is that here each element E will come in at most So the frequency of each element would be 2 because each element appears essentially in 2 sets corresponding to vertices. We discussed that if the frequency is f, there is the f approximation for set cover that we discussed previous time. So there's the f approximation if f is the maximum frequency of an element. So here, this one that we are getting is not. So this is the second approximation. This one is not touching that part. I believe, I mean, there might be some generalization also that consider the frequency, but this is the one that considers the. So there are 2 other cases. The other case is says that if all the sizes are small, then this algorithm gets actually back f of log of maximum. So if all of them are constant, you can get constant factor approximation. So in set cover, we can get constant in 2 cases. One is the case that this frequency of each element is small. Here, the size of the sets are not small necessarily. But sometimes also the size of the sets are small, then we can get constant. And this also gives that result. So that's a strong result. So here, again, max of j belonging to u f of j would be the maximum size of the sets in the set cover problem. So we have the same things here as well. So in this reduction that we have mentioned, again, the same thing. So you can see what is the f of s. F of s, again, would be, f of individual guys would be the number of elements that it covers. That's the thing that it can add, essentially.
One question. So, hold on. So here where you define like upper market like maximum. So for set cover, this wouldn't give you a log of that. Like why would this be log of that?
So this would be the log of it depends. I mean, what is n? So n is if the number of sets. This one gives essentially the log of the number of elements. Yeah.
Yeah, but for set cover, when you have a log of an approximation number of sets.
I think the previous one that we had it. I believe there. I believe that was the number of elements there.
That was also the
yeah. But we can get log of the number of sets as well. That we can get it. I think there might be some reduction from one to other.
Okay.
But I mean the general one is this one essentially. The other case you can get it from this. We are seeing this type of things, log of the number of elements versus log of the number of sets in all of these problems. Unique coverage has these things. Set cover has this one, and lots of them you can get. In one of them is non-trivial. The other case you can just do some reduction to the other one. You can do some pre-processing and other, then you can do that. That's a typical thing that it happens. So another interesting problem again, these are non-trivial problems if you think about it. So this is an exercise that you can also solve. So let's consider another problem. It is called capacitated set cover. By the way, these are all versions of set cover that are important. In the capacitated set cover, we have this additional capacity constraints on that. How many elements a set can cover? Good. So here, like in the capacitated set cover, a set can cover, I mean, it can have lots of sets, lots of elements in it. But when it comes, it can actually cover only like 5 of them. So if you may need to add essentially, so if you want to cover the whole things, like for example, if you want to just cover this one particular set, head element and the capacity of this guy is 5, then you need to use 2 of these. So this is the one that is called capacitated set cover, capacitated set cover. And again, you can think about it, for example, this is like, you can think about it, lots of network things that this guy can give a coverage, but it has a capacity. You can consider like wireless antenna or others. Again, this, it can cover the whole area, but at the same time, it cannot give the credit, it cannot, if there are some of these guys are there, then it can do it. But if all of these guys are there, it cannot cover all of them because it has a capacity in terms of traffic, etc. And then this is an important thing. And then this is actually a good exercise to show that this problem is indeed also can be solved by submodular setcover. So it's a very important and strong problem. So let's talk about so let's talk about another important, which is a very general set of problem. It is called submodular tree coverage. So you can, I mean, think about, so in some sense, whenever the problem, this is somehow the general summary of everything. If somebody gives you some problem that you think that this problem is a the greedy algorithm should work, like set cover, it means that most probably you can define the f function for that, the submodular function, and then use the Woosley theorem to show that this is. You don't need to design your own algorithm and other stuff. You just try to think about this f function and then just use those. And there are lots of papers. If you don't know, not all people know about it, and they just have one yet paper about using set cover ideas instead of just using this. This is another such kind of general function. Submodular tree coverage problem, which is also called a polymatroid Steiner tree problem. So what is this problem? So this problem is this one, that in the submodular tree coverage problem, you are given a general tree T with a set of leaves denoted by U. So this is a generalization of the previous case. So this is a tree is given to you. And this is the set of leaves, like it is U. So this is U1, U2 to U. N. And there is a function which is defined on the set of leaves. So a function f is defined. So for any subset of these guys, you can define the f of this guy, f of this. Now, each edge E of this tree has also a cos C. This is edge E. It has cos C. Now, you want to find a subtree S with minimum cost. So you want to find a subtree of this guy. I said it should contain the root. Maybe this. So here you essentially you want to find a subset of these guys. Some of these some of the edges such that they form a subtree, such that f of S of L, what is S of L? So this is for this subset, these are the leaves that you have. This is called S of L. So we want to have essentially f of S of L is equal to, like, or say, I will optimum. We will put it just generally a star for optimum is equal to f of u. This is again these are like very powerful theorems. We will sometimes actually call them frameworks that not only solve one problem, when you get it, then you solve the whole set of problems. And this is the power of submodular functions. That's the reason. So in some sense, like that Woosley is from 1982. So it's a very old one, and it gives one theorem with the submodular definition that can solve lots of problems. You don't need to solve individually the problem. This is like a hammer, big hammer that can solve the problem right away. And that's the thing that is important. The same thing also for Matroid. Matroid is another thing that has such kind of properties, and the people love it. But submodular, as I mentioned, this is one of probably early version of submodular. I think maybe this is the place that it is the most famous. Submodular is the most famous because of loose leaf. So lots of people actually may not know about it. Maybe I didn't know originally this one was like so strong too. So here is essentially the generalization of that problem. Submodular, that was submodular set coverage. This is submodular tree coverage. You want to find here a set of this tree, a set of edges, such that the leaves that you will cover, you will reach, f of s of n is equal to f of u. Then this is a paper by Kalinsk. I mean, not cover the root. I mean, it should start from the root. I think you should see that. I think it is probably you can even. I mean, the issue that if the root is not included, then it is not. It would be a forest instead of the tree. But the issue that if you don't come to the leaves, there is no benefit to you. Yeah, I mean, you can have part of it. I assume, I mean, you should check it. I don't want to say either way, but say for now, if you are assuming the root, but it may work if there is no need to be essentially root is included. And you know, actually, that's actually a simple thing for this type of thing. So these two problems are equivalent, whether root is included or not. Because if not, you can include any. We know that this guy has a root system too. So then you can run over all the vertices as a root and solve the problem and take the minimum. So that's a typical thing. If this is the thing, the rooted problem versus non-rooted problem. So essentially, Kiara's point was that whether always this guy should contain this R, or maybe there is some other things like this. Maybe you can start from here and do that, and does not contain the R. But anyhow, we know that this guy has a root, but so this is R prime. So we can assume we can try all possible nodes of this tree as the root and say that it should include the root. And if you have the procedure for that, you can solve the procedure for everything. This is one way that say the rooted version is more general than this. We are seeing this one, lots of other problems. Sometimes you can do the reverse as well and say that the unrooted version also can solve the rooted version, not all the time. Rooted generally is a bit more general. But anyhow, so you should say for now it should contain the root, so no such case. And you want to have some of the edges such as f of SL is maximum. Now, let's see what, so what do they prove it? They say that there is, and again, I think the only condition that we have is that if, yeah, so they say essentially there is a polynomial, log of 1 plus epsilon n log k. What is n here? N is the, like actually, I think this other one is, this is the place that this one is not giving the things. So if you come here, I think I have defined n better here. Yes, so good. Log of k, okay. K is the same as before. So the log of k is the maximum size of the sets, and n is the size of the tree. Good. Or you can say actually, if there is no degree of vertex 2, n is essentially would be the number of sets. So n is the size of the tree or the number of sets if there is no degree 1 vertex, degree 2 vertices on the tree. And say for now, n is essentially number of sets or the size of the tree. Good. Here, now let's go back to that other things because I didn't want to change this one. They say that, so as I mentioned, so here n is the size of the tree, and k is the same parameter as we have talked about it. Individual, if consider each of them individually, what is the max of them? this algorithm would be essentially log n times log k. And say generally you can consider define another n as the input, which is the maximum of all n. This would be log n square essentially. Good. So log n to the 2 plus epsilon. There is this algorithm, this submodular tree coverage problem, which is a good. Now this problem, it generalizes a few problems. In particular, it generalizes the group Steiner tree problem. I define this problem. But for this group Steiner tree, we know that you cannot get log n to the 2 minus epsilon. No such thing is possible. Actually, there was a Fox paper. I mean, we had these things as well. It is you can get lots of this one that they show that you cannot get essentially log n to the 2 minus epsilon. There is no such thing under some complexity assumption. However, we had these things, lots of these things that the lower bound is this. It generally means that you can do some slight improvement. There was, I think, the Fox paper that they get it log n to the 2 over log n. So you can actually get log n to the 2 over log n. And this is actually, I think we had it and we had some approach. It didn't work. We believe that it is possible before them. And we tried there, but our approach actually was a more LP approach. It was not easy to do that. However, they have used a combinatorial, and it's very simple. We didn't believe that actually can get into Fox, but I mean, got actually Fox. It's a nice result. That you can get log n, and they can get it also something for directed Steiner tree. I think this was Vishwanath Nagarajan. He was my co-author. I should remember his name, but he's at Michigan. So you can search, you can find it essentially. This was, I think, a Fox or stack paper. Most probably Fox. But anyhow, whenever you will see 2 minus epsilon, it means that probably log n to the 2, for example, here, over log n should be possible. And they can show that there is such approximation for group Steiner tree. And this problem is more general than that. It means that there is no approximation better than these things that I have mentioned for the problem. So this is almost tight. Again, that would be interesting. I don't know the current state of the art. I mean, like I don't remember whether this epsilon can be also removed from this, or can we get this log n to the 2 over log n? That would be actually interesting. Maybe not at that time, but now it is given several, I don't know, 2005, 18 years before it was such a thing, making this one tight the same as Steiner. Group Steiner tree would be interesting. Let's say why this problem first. I mean, is interesting. Like why this problem is a generalization of set cover, a submodular set coverage. So that would be a very simple case. So consider this one. The submodular set. So I'm talking about the submodular set coverage. So in the submodular set coverage would be actually easy. So for each of these guy, I will put essentially each of this guy E1, E2, E2, E2. And this is S1, S2. So the submodular set cover will be a special star case of this example. Because there, I mean, essentially, what was the goal? You want to find a set of sets such that f of these guys is equal to f of u, and some of the cost of these guys are meaningless. Good. Now, what are the sum of these costs? Some of these costs would be essentially just the sum of the edges that you are selecting to this. So essentially, those guys that you are yeah. So this is, let me just okay. So yeah. So here you want to just select essentially a set of these guys such that Essentially, a substar of this guy, I want to select it as the final solution. So submodular set cover is a special case that essentially the tree is just a star. And of course, there we had a log n approximation or log k approximation. Here we have another log n extra. Another problem, which is also is a special case of this submodular tree coverage, is the group Steiner tree. So what is the Steiner tree essentially? So in the Steiner tree problem, you are given so in the Steiner tree problem, you are given a graph, and we are talking a lot about this problem. You want to find essentially, so we have some terminals here. Not all, some of them are, some of the points, so some of this is the graph, and there is the edge between this, edges between these guys, and each of them has the cost. So this E has the cost C. You want to buy a set of edges in this graph with minimum total cost. So you want to buy a set of edges with the minimum total cost such that all these terminals that I have drawn by like a square, they are connected. Again, terminal are the subset. The rest of the vertices are called Steiner. Each edge has a cost, and you want to essentially buy a set of edges such that you will connect everything. Connect all the terminals. This is called Steiner tree. Now, there is another problem, which is generalization of this. It is called group Steiner tree. What is the group Steiner tree? So here, it is essentially, instead of each terminal, a subset of nodes are given. So this is not just one node. So this is not one node anymore. Instead of one node, you may have a subset. So we don't want to connect just a terminal. Essentially, we have instead of one terminal, we have a terminal subset. And I'm saying that, okay, this is one terminal subset, this is another terminal, and they may have actually intersection. Each of these sets are just some set of nodes in the graph, and they are not necessarily connected. So these nodes might be someplace here in the network, the other one someplace in the network, and so on and so forth. And they may have actually intersection. I want to just make sure that from each terminal set, at least one of them is connected to me. So I have a choice to connect this guy, for example, here, or I connect this other guy. And these two guys might be quite different. I decide which one. I don't need to connect both of them. For each terminal set, I only need to connect one of these guys. Say these are because of some backbone, they are already connected. And I want to say just go to the one that is closer to me. And I choose this one. This problem, so a Steiner tree itself, actually, you can solve it constant. So for a Steiner tree, there is a constant factor approximation. The best one actually is 1.39. This is the best paper ever in the stock. For group Steiner tree, so there is a Steiner tree. This is age weighted. There is a age weighted. There is age weighted. There is a node weighted Steiner tree, which is log n approximation, which is essentially equivalent of set cover. There, instead of set of edges, the costs are not on the edges, are on the vertices. There you can get log n approximation too. If this is edge version, there is a node version that it gives essentially log n approximation. And finally, the group Steiner tree. For group Steiner tree, actually, there is a, as I mentioned, there is a log n to the 2 approximation. Actually, this is, this is not quite precise. There is a log n approximation on trees. So for the group Steiner tree, there is a log n to the 2 approximation on trees. And essentially, this is the idea that as we discussed this submodular set cover, we get log n approximation. The fact that from each of these subsets, you need to choose only one of them. This is the one that gives you an extra log n factor, and this is log n to the 2. And let me say why, actually, this is also interesting, why this problem is, let me just say this one. Yeah. So let me just say this one, and then we can finish this. So consider this is the group Steiner tree. So the group Steiner tree on tree is what? So you want to find a subset of this tree such that each of them, again, let me just draw it. So this terminal set is this, for example. So this is one terminal set. The other one, it would be another terminal set. And so on and so forth. So the goal here is to select a set of edges here. For example, here would be like this. So let me have another group as well. Maybe this is another group as well. So in this case, that would be something that you want to draw, maybe. So you want, in the group Steiner tree, you are given a tree, and each of these, if you consider the leaves, I mean, they may have some different colors. And like a terminal set contains a set of these leaves. You want to buy a set of edges here, such that from each terminal set, at least one of them is connected. So here, for example, as you mentioned, from the purple, from this brown, and from this green, I have connected all. And you want to find the one with the minimum cost. This problem is a special case of submodular tree coverage. Why? Because you can essentially, for any tree, you can say that the leaf, how many groups does it cover? So again, the f function here would be essentially for S of L. It means that how many terminal sets is covered. So this is for group Steiner tree. So if you want to group Steiner tree, if you want to mention it as a special case of submodular tree coverage, that's the thing. So we say that for any tree that I will select, the set of SL, you see that how many groups you have covered. If the number of groups is equal to the number of all terminal sets, then essentially you are done. And you want to solve the problem. And as I mentioned, this is a general problem that actually can solve this problem. So this is another, beautiful things that you can use it. And these are the two very general theorems, again, like a hammer, that you can do it, and lots of special cases can be just mentioned essentially in these things. Later on, we will talk about it. So far, we are talking about trees a lot, star trees, this one. Later in this course, we will say that actually there's a lot of effort to say that almost all problems, instead of solving them on the like general graphs, you can actually solve them only on the trees. But when you solve them on the trees, then generally you are losing a factor log n or something like this in terms of approximation. So that's the whole idea that the people tried a lot for lots of, we call connectivity problems or cut problems. There are something, it's a beautiful theory that has been built over 30, 40 years that essentially lots of graphs, you can represent them somehow by tree. You may lose something by log n, and this is the best that you can do it, but it solves the problem much better. In practice, actually, you may not even lose this log n factor. Lots of the time, you can do it much better, but in the worst case, this is log n. So that's the idea that we talk about trees, stars, a special case of event trees, and graphs, later the more networks, etc. But as I mentioned, then we said, oh, these are actually equivalent of to these trees that we are considering. Yeah, I think that's it.